As discussed, we're going to cover a lot about Wi-Fi 6 in our part of the presentation. And there were some other topics as well that are listed up there, things like IoT and some other things. So I will get into all of that. There's, again, 5G millimeter wave. That'll be in the second part of the day. We'll lead off into it at the end of our talk, leave you with bated breath during lunch. Let's see. So for anybody who has kind of wandered into this presentation or this seminar without knowing anything about octoScope, I do have a very brief introduction. There's a lot of detail kind of in the back there from the frame guys. You can see our system up here, and we'll be happy to talk to you about it during the break or afterwards, whatever you like. But just in general, what do we do? Anybody who's been in wireless testing for any length of time knows that there's a lot of different ways that people do wireless testing. Two big ones are the use of either shielded rooms or anechoic shielded rooms or walk tests. Both of those have their pros and cons. Shielded rooms are really good for, again, obviously shielding and keeping yourself free of interference, but they're big, they're expensive, it's hard to get very many of them. Walk tests are great, they're sort of accessible to everybody. Problem with walk tests, of course, is that they're completely exposed to the surrounding environment, susceptible to interference, very hard to get reproducible results from one test to another. So what we do at octoScope is we try to combine the kind of best of both of those testing methods into what we call wireless personal test beds. They look something like the one shown in the picture here. You can see a small one in the back there. They go anywhere from basically the size of the one in the back to the one that you're seeing here, which would be sort of a medium-sized one, and they can get much larger. We'll talk about how they get larger as we go through the presentation. The benefits in general are that we're able to reduce the time to do typical tests, especially things like walk testing, from what might be days or weeks to do some tests down to hours. The size of the systems means that we're always able to achieve very high signal strengths, meaning we can get maximum MCS, maximum number of streams for Wi-Fi technologies. But in addition, and this is what makes it somewhat different from typical sort of shielded room testing, is we're also able to test real-world type environmental conditions through the use of controlled interference generation, multipath emulation, all of which we'll talk about a little bit as we go through, and some of which we'll demonstrate. We're widely used. If you don't know of us, and are in the industry, you'll probably run across this eventually. We're used kind of throughout at this point, all the way from chipset vendors through equipment manufacturers to operators and even many test labs. In general, when we're talking about our systems, and the reason I'm going through this is that this presentation has a lot of embedded demonstrations. So we want to do a lot of demos, make it a little bit more hands-on and kind of see what we're really talking about. But in order to understand what's happening, you have to understand a little bit about what the systems are. So that thing that is right over on the other side of the screen, we want you to understand what you're looking at. So our test beds are made up of a number of different components. There are shielded semi-anechoic chambers. There's one there, that's a big one of our biggest ones. There's one in the back, that's a medium-sized one. Those are the kind of the main components. Then there are programmable attenuators. The attenuators are used in order to essentially create distance between the devices and the network, so you can do rate versus range tests, and you can do a lot of other sort of very interesting tests having to do with roaming and creating of mesh topologies, and again, we'll talk about it in more detail later, but just so you have some idea. We have the ability to emulate multipath through the use of a multipath emulator, which we don't have in this room, but it looks like the picture that's shown on the slide. We are also able to create controlled interference, and again, this is a really important test. People use this for any number of reasons, and we're going to actually do two demos of interference generation and interference testing, so you'll see how that works. And then finally, we have test instruments that we call PALs. And these test instruments are kind of the heart of the systems that a lot of people use. Again, it's very important for you to understand in order to understand what's happening in some of these demos, for you to understand what the PALs do. So the PALs are our test instrument that can be used as partner devices for whatever test you might want to do. So for example, if you're a company that is testing an access point or residential gateway, you might want to test that against, or you'll need to test that against some sort of client device. One thing you can do is go out and get an off-the-shelf client device to test it against, but that requires you to sort of pick a device and make sure that that device is the one that's always the one that you're comparing against, number one. And number two, the device itself will only do what it will do. That is, you can't force it into modes and test various specific things you might want to test. The PAL is an actual Wi-Fi device. It's based on a real chipset. I'll talk about it a little bit more. But it's based on a chipset, and we obviously make it possible for you to control it in a great amount of detail. So for example, you can force it to specific data rates, you can force it to specific bandwidths, you can force it to a specific number of streams. So you can do a lot of things, and it also produces a lot of useful information. So you can look at the signal strength, you can look at, again, the number of streams, the MCS rates, that sort of thing. So, and you'll see all of that in the demo. So that's what the PAL is. All of this comes together in what we call a personal test bed. Again, you're seeing one here, you're seeing one in the back of the room, and everything that is in there as it's put together is all under software control. So you'll see that, and all of the devices expose a REST API. And the APIs can be used to build these test beds into any sort of automation framework that you might have. And the reason actually I want to emphasize that from the point of view of this seminar is that anybody who's seen us in the past might have seen us do demos where we open up the software, this picture here, and then we configure things in the software, and then we run the test. In this seminar, what you're going to see is a lot of automation. So we're going to use the software really only to view the test. We're going to use automated scripts to run all of the tests, and we have been working quite a bit in recent months to make our automation much more powerful, much more flexible, and that's the reason we've kind of, even on our own, shifted over to doing a lot more automated tests than manual tests on the browser. So just with that as background, we want to kick this off now with a little bit of actual sort of real-world tests so you can see what this looks like. And what we're going to do is what we call kind of our classic rate versus range test. And I see that, hold on, this is actually visible to you guys as well. I'm just trying to get rid of it, sorry. So this is a rate versus range test. So, and I'm going to walk you through this diagram, the diagram that's on the screen just a little bit now. You're going to see it a lot more times as we go through and do all the tests. So spend a little bit of time on it now, and then you'll understand it every other time you see it. So the big box there is the box that you're looking at over here. It is our largest size box. It has a turntable in it, and it has access points inside. Chuck, you want to open it up and show people what's in there? So that's what the inside looks like. You can see the turntable, turntable. And there's also the AP that's shown in the picture. There's actually a few APs in the box itself, and there's actually some other stuff for 5G testing, which we will have described to you later. But for the purpose of this test, there's really only the AP on the turntable that we're really interested in. And then there's a set of PALs, and those are underneath, down there, where Chuck is pointing.
Yeah, there's some underneath, and there's some other, there's one of the iGen is on the side.
On the side. And the PALs are connected into the box via RF cabling through these attenuators. And in this test, what we're going to show is the use of the system in order to test rate versus range. So this would be, how the device is able to perform as it gets further and further away from the access point. And the way we cause it to get further and further away is to ramp the attenuator that is shown here next to this PAL. So not sure, the animation is not working. Oh, there we go. So it looks like that. So this test looks like that. It's a very simple test. We're running traffic from our server, actually, through the access point down to the PAL. And as we run that traffic, we're going to slowly ramp the attenuator, and you'll get to see what happens. So we are ready to go. And this is our software. And I will find that test, which is the throughput versus range test. This, as I mentioned before, I'm kind of magic at this point, right? I didn't actually do anything. Chuck over there just ran a script, a Python script, which set up the attenuators, set up the PAL, started running the traffic. It's also set up the system to do all the ramping. So what you're looking at here is the throughput between that access point and that PAL, and as the attenuator is increased, you can see the throughput dropping. So this is the rate as a function of essentially distance. Just a real quick introduction to the software, and I won't go into this in great detail, but you can configure everything via the UI. So you can see that we've defined a single traffic pair. In this case, that's going between our server and our PAL, shown here. You can see that we have set up a certain path loss profile. So in this case, we started at 20 dB of attenuation. We're stopping at 70 dB of attenuation, and we are stepping 5 dB and 5 dB steps. And so, oh, actually, so we can start it. Well, anyway, it doesn't matter. So you can see what we get here. We are able to get, as I mentioned, from the PAL, a lot of statistics. So, for example, here was the RSSI as received by the PAL as that traffic went on. You can see it's starting at about negative 60 dBm and dropping down to close to negative 90. And we're also showing the RSSI not only on one chain, but on all 4 chains in this 4 antenna device. We've got the data rates. So these are the actual data rates, MCS values, the number of streams, the bandwidth. You can see the bandwidth starting at 80 megahertz and then starting to drop off as the attenuation increases. And you can see the congestion on the network. So a lot of information, and that's the basic test that we would do in our system. And we're going to go through a lot more of this as we get into Wi-Fi 6 and the other kind of main points of the presentation. Any questions on that? I mean, was that sort of clear? I want to make sure everybody really understands what's going on here so that as we go through, nobody's confused. Okay, roughly looks okay. So again, at the seminar, this is what we have. So what you're looking at here, Chuck already opened and showed it to you. But we've got that box, we've got a bunch of PALs. There is stuff from Advantest, or I've written W2BI here just because it's shorter, but they have both their 5G and 4G equipment, and they'll explain that in detail to you later in the day. And the other thing that we have that we will be talking quite a bit about is, and I mentioned the PALs, and the reason I want you to understand what the PALs is so that when I talk about this thing, which is the PAL 6, you'll know what I'm talking about. So the PAL 6 is our Wi-Fi 6 or 802.11ax product. And in addition to being an 11ax product, it's actually a new type of deployment model for us. So instead of deploying our 11ax product as one of those metal boxes that we pointed out before, we've actually deployed that in the box itself. And again, I'm going to talk about that in more detail, but that is an important point. So when you see this picture, the reason that this PAL 6 is shown being inside the box is that it is literally built into the box itself. It's an architecture we call the smart box architecture, and I'll describe it in more detail. So that thing is made up of what's shown here in this little inset. And
yeah, it's actually underneath the foam here, so it's, as we said, it's part of the box, but it's not kind of intrusive in any way, right? So the cable isn't shown here to antennas inside the box or connected.
Yeah, And that will be, as we go through this, it's going to be a lot more obvious why we've done that. So now to get into sort of the heart of the matter. So what we're going to talk about today, we're going to talk about Wi-Fi 6, just some overview, what's going on there, what we're doing as a company. We'll talk a little bit about mesh testing and band steering, not a lot, just a bit, so you can understand some more complex architectures. Also, that conversation leads us sort of naturally into the smart box, why the smart box architecture with the PAL embedded into it exists now, and then some technology that we call synchro sniffing or synchronized sniffing. Again, highly related to the idea of having these PALs embedded in the boxes themselves. So let's start with Wi-Fi 6. Up until very recently, I think everybody was just referring to this as 802.11ax because that's what we all do. But the Wi-Fi Alliance has decided that they wanted to make things more friendly, so they've come up with these things. So anybody who hasn't heard that before, that's what Wi-Fi 6 is. Wi-Fi 5 is AC, and Wi-Fi 6 is 11ax. So what was 11ax all about, or Wi-Fi 6? It's really, so it's called the High Efficiency amendment to the standard, and it's a bit of a change for Wi-Fi. It's a move away from kind of the relentless increase in throughput that the Wi-Fi standards were going after all the time. How can they get more and more bits through the pipe? And the reason for that is that Wi-Fi is used more and more these days in crowded, dense environments, things like multiple dwelling units, for outdoor uses, that sort of thing, where you've got a lot of users on access points. And although, high throughput is great, the problem with it has always been with Wi-Fi that when you get a lot of users on a single access point, the technology spends quite a bit of time arbitrating which user gets access to the medium at any given time. And the efficiency of the network drops fairly rapidly as you get a lot of users on. So another way of saying it is, it's great to have a fast car, but it doesn't really help you if you're spending a lot of time at lights. So the idea behind Wi-Fi 6 was is to improve the average throughput. So this is the actual statement of the goals. So 4 times the average throughput per station in a dense deployment scenario. So again, the idea here really was focusing on if you've got a lot of users, how can you handle them efficiently? For the same reason that the network becomes inefficient, it also, latency increases pretty dramatically if you have a lot of users on a traditional Wi-Fi network. This all has to do with how Wi-Fi devices access the channel. They're always listening for other devices. They're always backing off and waiting for the channel to be clear. So if you do have a lot of users and you have latency sensitive traffic, you can have trouble getting it through, in the required time. So they wanted to improve the latency and improve the efficiency and interference management capabilities. So from a technology point of view, Wi-Fi 6 is made up of a couple of key things. Even though I said before it's not really a focus on throughput, there is, thank you. There is a change to a few new MCS levels, 10 and 11, that do provide increased throughput. But the real focus and the real sort of interest in Wi-Fi 6 has to do with the multi-user operation. So Wi-Fi 6 is a Wi-Fi technology that truly allows for an access point to handle multiple stations simultaneously. And this really hasn't been available before. 11AC had the start of it with some multi-user MIMO capability, but it was not, I think, really widely used. But with 11ax, that's really the focus, is the multi-user operation. There's 2 ways of going about it, which can actually be combined. 11ax has multi-user MIMO, again, like AC in the downlink direction, but also in the uplink direction, which is new for 11ax. And it also implements what's known as orthogonal frequency division multiple access, OFDMA, which is technology that's used in cellular networks, and it's how they handle multi-user traffic. So I will say that from what I've seen so far, the real interest in 11ax is OFDMA. Multi-user MIMO has still some level of interest, but the Wi-Fi Alliance is, I believe, only testing still downlink OFDMA. So the real multi-user operation that's going on in 11ax, especially in the uplink direction, is OFDMA. We'll talk a little bit about what that means. There's a couple other things. They did essentially increase the symbol times by quite a bit in 11ax, and the reason for that is that it provides more kind of a more robust system if you have large delay spreads. So again, if you think about Wi-Fi now being used more in outdoor environments with lots of users, this all makes a lot of sense, right? Why you would have those two things together. You want to be able to handle a lot of users, and you're outdoors, you may have signals that are bouncing off of buildings as opposed to what you have in a home where it's walls and things like that. So you'll have longer delay spreads, and you want to address that by having longer symbol times. And then finally, they added or picked up from previous 802.11 technology something called BSS coloring. And BSS coloring, actually I have a little bit of a slide on it here I won't talk about it anymore after this slide, but is something that allows you to operate a little bit more under your own control in an environment where you have a lot of different networks simultaneously operating. And again, all has to do in this case with what it looks like as you start deploying Wi-Fi more and more densely with lots of different networks. So BSS color kind of looks like this. What I'm showing here, I used colors because it's BSS color. So I've got two of those kind of pink networks in the left and the middle. So think of this as one system with the same SSID, an office or something like that, and then another network nearby. And let's say these things are co-channel. They can hear each other, and now they have to decide what to do about it. In traditional Wi-Fi, if you can hear another Wi-Fi device, you can decode it, and you recognize it's Wi-Fi, you need to back off to it. The idea behind BSS coloring is that you actually give the access point information about whether or not the packets that it's hearing are part of its own BSS or some other BSS. So it can tell, for example, so this access point here in the middle is really handling this client. This client is actually talking to this access point, but its signal, of course, goes wherever it goes. This access point may be able to hear it, so it can tell that's one of my guys. But when this client is talking to this access point can hear that that's somebody else's guy. And it allows the access point to decide what it wants to do about that. It can make a decision about whether or not it wants to back off, or if it wants to take a hit and signal noise and operate simultaneously. So it's just a way of giving access points a little bit more control over how they want to handle their own traffic and how they want to handle somebody else's traffic. I won't talk any more about BSS coloring. Multi-user MIMO. Multi-user MIMO is, as I mentioned, a technology that was in 11AC and is also now in 11ax. It's a technology that, sorry, just from the point of view of the kind of tests that we're able to do in the test beds that I've been describing, we do those tests all the time. We don't have it set up here, so I just want to show you some quick results, and I'll describe a little bit how it's done. So in this case, it's a very, very similar test to the one that I showed you before, the rate versus range test, where I would run traffic between an access point and a PAL. But in this case, I'm going to run traffic from that access point to two PALs. So I'll associate two PALs, like two clients, and the traffic can run to them. And I think, Chuck, you were going to show how this is done. When we show these pictures, I've got one antenna. It looks like there's one antenna here. And the way multi-user MIMO works is by forming beams and using the beams to separate the signals in space. So clearly that can't happen with a single antenna. So it's actually important to recognize that when we show these pictures, anything that looks like sort of a slightly heavy line or a slightly heavy arrow like that is actually four things. We always consolidate 4 antennas or 4 cables or anything like that into one to avoid making the diagrams too cluttered.
So, for example, the multi-user MIMO may be using these 4 antennas, but what we'll do is that'll be set up most likely in a SISO environment. It will access this antenna 0 and antenna 3 in the back, so we get some spatial diversity in order to be able to do multi-user MIMO. I mean, ideally you could do it with 2 antennas from opposite sides of the chamber. Again, it depends on how the chamber is wired. In this particular case, all 4 of the antennas represented by that red line coming from the PALs with the antenna on it are able to get enough spatial diversity there to do multi-user MIMO.
And what that looks like, I'm just going to show you some results, and then we'll move on to some of the more interesting technology in 11AX. But what that looks like is this. So as Chuck mentioned, we often do that test in just a single stream mode. So what you can see here is this is not rate versus range, right? So this is just throughput as a function with multi-user MIMO turned off. So I've got down here the 2 client devices, and this is the aggregate throughput. So the single stream data rate for 80 megahertz 11AC is about 433 megabits per second. So you can see that the aggregate traffic is, roughly 400 megabits per second, a little bit less, and essentially each of the 2 devices is sharing that bandwidth, because that's how Wi-Fi works, right? So one guy gets it, the other guy's listening, the other guy gets it, and then they share back and forth. When we turn multi-user MIMO on, it's actually pretty impressive to see that what happens is that actually the individual throughputs come up to just about the same level as the aggregate throughput with multi-user MIMO off. So we're actually seeing the ability for the access point to communicate simultaneously with both devices. You can see that the aggregate throughput in this case is, up near 700 megabits per second. So this is what the big chart shows. So with multi-user MIMO off, we're 350, something like that. And with multi-user MIMO on, we're more like 700. So, you can actually, even in this, chambers the size that we have, you can actually have enough separation of the devices and their antennas in order for the access points to form beams and do multi-user MIMO.
Very likely with that data.
Yeah, no, it did.
That would be cabled up exactly the way that Lee showed in that earlier picture. For all the PALs, you only need a 1 by minor, we need 4 antennas on one side.
Okay, so let's move on to OFDMA. This is kind of where all the buzz is, where all the real excitement is. As I mentioned before, OFDMA is technology used in cellular communications. It's like OFDM, which is what 11AC uses, but this is multiple access, not just multiplexing. So the difference is that on the left-hand side here, so in like an AC system, you've got your channels, your Wi-Fi channels, and at any given time, one of those channels is allocated to a user, and the access point can allocate channels to users as it sees fit, or as the clients are able to access the medium. But that's what it always looks like. So one user gets a channel at any given time. OFDMA lets you do this. So what you're seeing here is a two-dimensional plot, right? So this is time on this axis, frequency on this axis. You're seeing the individual subcarriers that make up the OFDM signals, and what the access point is able to do is actually allocate just certain subcarriers to certain users, and then different subcarriers to other users simultaneously. So you can see that in the first kind of time chunk here, you've got 2 users that are allocated some spectrum. So this channel has been broken in 2. So it looks like user 0 and user 1. In this next time chunk, user 2 got the whole bandwidth, but in this third one, it's actually been broken up. So there's 1, 2, 3, 4 users getting it. So that is how at a very high level, OFDMA is able to allow multi-user operation. So it's really it's in the frequency domain, and it allows the access point to allocate spectrum simultaneously to different users in the same channel and at the same time. The interesting trick is how that works in the uplink direction. It's kind of easy to think about in the downlink direction. Sort of the AP is in control, and the AP can decide and do whatever it wants. But then you think about, well, okay, but what do you do in the uplink direction? How do the stations figure out what they should do? Sorry, by the way, because I'll probably use it later. Those little chunks are called resource units in Wi-Fi. They're called RBs in cellular communication. Resource, what is it? Blocks, resource blocks, right? Yeah, I don't know why they decided it needed a new word in Wi-Fi, but so the question is, how did they decide what RU they're going to use in the uplink direction? And the answer is that there is a whole trigger frame mechanism that goes on. So once you get into, if you already have, about this, if you're just starting to hear about Wi-Fi 6 for the first time, you will hear about the trigger frame. And the trigger frame is what's used to do the coordination across multiple devices for uplink transmission. So it includes all kinds of information that tells the client devices what allocations they got, so what RU they should use. And it also has information about power control and timing. And there's some very, very strict requirements around synchronization, which I'll talk about in a second, for those devices, which is really new ground for Wi-Fi for 802.11. But it looks roughly like what's shown in the picture here. Trigger frame is sent. Based on that trigger frame information, all of the stations will respond with these uplink packets, again, simultaneously. And then also for efficiency purposes, the AP will actually act them all together. It doesn't have to act them individually. So when I said that it's kind of a whole new regime for 802.11, there was some pretty precise stuff going on in response to this trigger frame. So again, because you've got multiple stations transmitting at the same time, you have a lot of the issues that the cellular people have had to deal with for a long time. Things like making sure that you don't have close-in devices with whose powers will be received at the access point at a higher level, swamping far away guys. So you have power control requirements that didn't used to exist. You've got timing issues. So these are the big 3. There's transmit power accuracy. So devices are now required to have a certain ability to control their transmit power. There's a timing accuracy. That timing accuracy is pretty tight. It's within 400 nanoseconds of the required time. So the trigger frame comes, and then there's what's called a standard interframe space, SIFS time after that, and that's when the uplink packets are supposed to come. So you have to be within 400 nanoseconds of that time. And there's also a carrier frequency offset requirement. So you want to make sure that your clock is not too far off of your neighbors, right? You don't want to be shifting outside your frequency space. And so the frequency accuracy, I put the actual node in here. It's 350 hertz for data subcarriers. So at 5 gigahertz, that's 0.07 parts per million. So some pretty tight requirements around how those devices need to be able to operate. The reason for pointing that out has to do a little bit with what I'm going to talk to you about some more when we talk about what the test beds look like in order to test that. I mean, how do you test that kind of thing? Where are we in Wi-Fi 6? Again, just in case anybody doesn't know, the the standard is actually, I'm not sure if there's anything past 3.0, there may be, but final amendment hasn't happened yet out of the IEEE, but as always, the Wi-Fi Alliance has taken what it existed and has already started their process for creating certification test plans. So they're actually, this slide used to say something like it's already started, but now it's actually almost over. Actually, right now, I think it's this week and next week, is the second to last plug fest for the Wi-Fi Alliance certification testing. So people are showing up with their access points and their stations, and they're running through a set of test cases. Again, I said this is the second to last one. The last one will be in the April timeframe, and I think the goal for the Wi-Fi Alliance is to be able to start their certification program sometime in the second half of this year. I think it's August, but it's roughly that timeframe. From our point of view, just to bring it back a little bit to testing, so we have been very active at those. We've been at every one of those plug fests since the first one. And the reason to point that out is to just make it clear that the systems that we have are already capable of doing 802.11ax testing. And the reason for that is that when I kind of ran through that list of things that we use to build up our test beds, things like the chambers and the attenuators and the antennas and that sort of stuff, none of that's really protocol dependent. And so people have been doing 11ax testing at the Wi-Fi Alliance in our test bed since the first one. As I mentioned, at the first one, we brought a test bed with us and wanted to see if it was useful. Since then, at every plug fest since, we've been getting requests to bring more of them. The last one, we had 8. I think we have more than that at the current one. And we have actually already fielded requests from the staff at the Wi-Fi Alliance to have their own test bed. So they're very useful, and people are finding them very, very handy for doing Wi-Fi testing, or sort of Wi-Fi 6 testing. I said before that the stuff that makes up the test bed is not protocol specific, but of course I introduced you to the PAL at the beginning. So obvious question would be, will there be a PAL for Wi-Fi 6? That one clearly is protocol dependent. The answer is yes. That's what we call the PAL 6. I mentioned it at the beginning, so now I'm going to go into a little bit more detail about the PAL 6. And I also told you that it's actually being deployed slightly differently as part of the smart box, and Chuck already pointed that out. So like all of our PALs, it's a real chipset. It's based on Qualcomm chipset, and it looks like what's shown here in this picture. It is made up of 2 5 gigahertz radios, which enable us to do either 8x8 MIMO in 80 megahertz or 4x4 MIMO in 160 megahertz. It's also got 2.4 gigahertz. By the way, just FYI, again, if anybody wasn't completely aware of what's going on in Wi-Fi 6, Wi-Fi 5 or 11AC ignored the 2.4 gigahertz band. It wasn't technically developed to operate in 2.4. People do build products, but from a spec point of view, it wasn't designed to work in the 2.4 gigahertz band. 11AX supports both 2.4 and 5. That's been of great deal of interest to people because I think people are hoping that that will help with the perceived congestion in the 2.4 gigahertz band. So it has both a 2.4 gig radio, 5 gig radio. Again, both are 11AX capable as well as backward compatible with everything else. And there is the way this thing is built. It's built to handle daughter cards for other technologies in this PAL. The one that we're working most aggressively on at the moment is our Bluetooth daughter card. So this will be a true Bluetooth device, actually 2 Bluetooth radios based on a Cypress chipset, actually. And they are able to actually do real Bluetooth traffic, handling a certain number of Bluetooth profiles, A2TP, things like that. So people can do Bluetooth testing in the same way that we do Wi-Fi testing in our test beds. So I mentioned that we're at the Wi-Fi Alliance, participating in all the plug fests. The goal there is to come up with a test bed that will be able to support 100% of the Wi-Fi Alliance tests for certification, so that people can use a test bed to do pre-certification of Wi-Fi 6 products. And it looks like this. As we've gone through again at every Plug Fest, and they've advanced from the easiest test cases essentially to the more and more complex ones, 4-station, uplink, OFDMA, that sort of thing. We have worked with anybody who was using our test bed and maybe they were having trouble with some test, and we've constantly been refining the test bed so that we can support all the test cases. And we're showing, so I'm showing you sort of what it looks like. It looks, again, a lot like the thing you're looking at there, except it's taller. It's got three chambers in it. I'll show you what's in them in a minute. And it has an RF instrument on the top. We don't have an RF instrument here at this, but the reason for that, just kind of the reason I went through all that stuff before, the reason for that is that all those sort of more complicated tests around power, carrier frequency offset, and timing are all tested using these, in this case, LightPoint. There's a couple others, but LightPoint RF device. So that's, it's more complicated than previous Wi-Fi Alliance test cases, which are usually done by analyzing PCAP captures, and the vast majority are done that way, but those pre-correction tests, known as pre-correction tests, need to be done using that. And so our test bed is made up of our things, and we're partnered with LightPoint as well. The block diagram is a little bit crazy looking, but just take a breath. It's not actually that bad. There's a lot of wires, but it's basically the 3 boxes I showed. So there's one on the left here, one on the right. The one on the left holds what are known in the Wi-Fi Alliance terminology as testbed APs. So when the Wi-Fi Alliance is done with their test plan, they will designate a certain number of APs as testbed APs, the ones that you need to test against if you're testing stations. And the one on the right is holding what are known as the testbed stations, so the other way around. And then the box in the middle is holding the device under test. So whatever it is you're testing, you can test against access points, you can test against stations, whatever it is. And there's a sniffer in there. Our goal is for that sniffer to be the PAL6 that I've mentioned before. And then there's the LightPoint instrument, and those are what these antennas here are connected to. That's what the testbed looks like for 11AX. So what we want to show you now, we're going to try anyway, is the kind of a very simple test of that Wi-Fi sniffer capability for 11AX. So I've kind of introduced you to the PAL, and I've a little bit introduced you to the smart box, although not in great detail yet. But what you know is that there is a PAL right here, where Chuck showed you before. It's under the foam in the box. So there's a PAL embedded in that box. You might have noticed when we opened it before, there's actually 2 access points in there. Those are early 11AX access points. And what we're going to do is run traffic between the 2 of them. Go ahead. Yep.
So we've got one of them in bridge mode, one of them's active. An endpoint connected diagram. Traffic between.
Yeah. So, there's not a lot of stuff out there yet to do Wi-Fi 6 yet, but that's why we have one of our access points just in bridge mode. So we'll send the traffic that way, and we will use our sniffer to sniff that traffic. So we go. Okay, so we can see actually traffic is now running between those 2 devices. It's pegged here, by the way, at roughly 900 some odd megabits per second because there's an Ethernet cable, 1 gig Ethernet cable on this setup. We can do this test with and see greater than a gigabit per second throughput, but not in this, unfortunately, this particular test bed, this configuration. So that's why you're seeing that pegging. But we do have traffic running, real 11AX Wi-Fi 6 traffic running. So I'm now going to just turn on the Wi-Fi 6 sniffer and start capturing those packets and grab that stuff and pipe it into Wireshark. We are having, I will admit, just a little bit of weirdness going on with this particular test. So what I can show you, real quickly here, is that although I can't. What I wanted to be able to show you actually was MCS 11, and if I get it working later in the day, I'll definitely show you MCS 11, MCS 9, something like that. But what you can see is the HE headers. So you can see us. We're capturing. This is 11AX traffic, and that's the PAL6 capturing those frames. So yeah, the beacons. So yeah, like I said, for whatever reason, we're having a little bit of strange problem here. And like I said, if we get it working a little bit better during the day, we'll be happy to show it to you. But what we're able to do at this point is to sniff the 11AX traffic, and we are currently bringing up our 11AX access point station modes the same way that the current PALs work for 11AC. And as I said, the Wi-Fi Alliance testing is this week, so we're at the Wi-Fi Alliance starting to test those modes as well. All right. One of the topics that was on the list at the beginning was IoT. So you might be asking, kind of what's sort of IoT related about this? And the answer is that Wi-Fi 6 actually has a very interesting potential role in the IoT, and I don't want to stand up here and tell you that I know what's going to happen with IoT, right? Anybody who says that is making things up. But we all know that there's a lot going on in that space. I mean, there are already plenty of things out there, and there's a lot of buzz around 5G and all the different aspects of 5G. And one of the things everybody's talking about is how either 5G or IoT or whatever you want to talk about in this particular context has to do with the use of so many other things now on networks, not just people. It's all kinds of devices connected to networks, right? Lots of things. So like in the 5G space, people are breaking 5G up into multiple different things, like the massive IoT and the enhanced mobile broadband and mission critical services, things like that. And in all of those different areas, there are things that are being attached to networks. But in the IoT especially, right, we're talking about things like sensors, security cameras, all sorts of things in people's homes, whatever. And they have lots of requirements around them, again, depending on what kinds of things you're talking about. Sometimes it's that you need them to be very low latency. Other times you need to be very kind of friendly to battery-powered devices and low power. So many different requirements, lots of different things. How many things? Just real quickly, you guys have all seen things like this before, but some interesting numbers, right? In 2015, there were, say, 15 or so billion devices that were connected to networks, depending on who you're talking to, right? So IHS says that number is going to grow to 30 billion in 2020. Intel says it's going to go to 200 billion by 2020. So it's a fairly big range, but I think we're talking about a lot of devices. And I think we already know it's true, right? I mean, even if you don't necessarily believe all of the hype, I assume that there's people here whose homes already have, wireless connected thermostats or security devices or cameras or doorbells or locks or something like that. I mean, you're already seeing quite a bit of it. But one of the interesting things about it, there's a lot of technologies out there. We all know these, right? LoRa, Sigfox, there's what's going on in the 3GPP. Lots of different technologies for connecting to the IoT. If you look at this is a plot from Cisco's VNI. And one of the things that's very interesting is that, outside of RFID and Bluetooth, if you look at their prediction out through 2020, 2021, Wi-Fi is still the technology that is connecting a lot of these devices. And again, just from my own personal experience, I mean, I know that to be true. I have things in my house, like my thermostat and that sort of thing, that are Wi-Fi connected. They come to your house, you just plug them in and connect them to your network. I mean, that's makes a lot of sense, right? Especially in residential environments and enterprise environments where Wi-Fi networks already exist. So, again, we're talking about things like doorbells, thermostats, lights, sprinklers, switches, sensors, that sort of thing. And the question is, okay, so Wi-Fi is great, right? Why not just use Wi-Fi? One of the problems, well, there's a couple problems, right, with Wi-Fi. One is that it's relatively power hungry. And again, if you're talking about battery powered devices, that's an issue for sure. And the other is that it's kind of a lot of bandwidth for some of these devices. These devices are fairly low, they can be at any rate, very low data rate devices, just sending a little bit of information every now and then, and allocating even a 20 megahertz chunk of bandwidth for that is kind of a waste. So Wi-Fi 6, though, actually does some things for you that make Wi-Fi a lot more friendly for an IoT kind of deployment. So I mentioned before that, kind of the big rationale or, kind of impetus for Wi-Fi 6 was efficiency and the ability to handle many devices on the network. So, of course, that makes a lot of sense in the IoT context. With OFDMA, though, as I mentioned before, you can now allocate, specific RUs, down as small as, I think, 26 subcarriers to a single user. So you no longer need to allocate an entire, even 20 megahertz of bandwidth to a single user. Right? You can go down as low as just a few subcarriers, meaning that you can be much more spectrum efficient using OFDMA to handle IoT devices. It also, because it's able to actually schedule devices and essentially, especially in the uplink, tell devices when they should be transmitting, you have much less of a chance of those devices when they access the channel colliding and then having to back off and that sort of thing. And so it's much more predictable in terms of when the traffic will arrive. And so if you have devices that really need to be getting their communications in on a regular basis, OFDMA is really excellent for that. And then finally, there's something I didn't actually talk about before, which is also part of Wi-Fi 6, which is something called TWT, Targeted Wake Times, I believe it stands for. And previously, it was possible to put devices to sleep in Wi-Fi, but their sleep schedule was regulated by the beacons. So they always had to kind of be awake, or at least not awake, but paying attention to beacons as they came through. And beacons come fairly often, meaning that the sleep time for Wi-Fi, while slightly effective, was not great if you're talking about small battery-powered devices that you want to last for a long time. This targeted wake time technology in Wi-Fi 6 actually decouples sleep times from beacons. You can actually tell devices when they should wake up, or devices tell you when they're going to wake up. And so you can have devices sleeping for very long periods of time now, much more battery efficient, much better for small battery-powered devices. So Wi-Fi 6 is a really important IoT, I think, technology as well. And this actually kind of leads us into the next topic I want to talk about, which is interference, right? Because once you're talking about the IoT, really almost anything these days in wireless, but let's say the IoT, when you're talking about things like hundreds of devices, more devices than we currently have, the question is, so what does that mean in terms of interference? Does that mean, hundreds of times more interference? Which is why interference testing is an important topic to be able to cover and to be able to do. So there's a question that's asked, like people say that, actually ask this question, right? I mean, will noise and interference throttle the Internet of Things? I won't play the little video. So we know it's going to be a fact of life. It's going to be all these devices. They're going to be in probably mostly unlicensed spectrum. And you will have noise coming from lots of different things, not only communication, but just the fact that you're turning devices on and off all the time. And I have some quotes here. I won't read them all. But, little snippets of them, right? When the number of devices increases by an order of magnitude, this will become a major issue. Already RF devices are shutting each other down due to interference, and the situation will grow worse when the IoT industry grows. This is a plot that just basically gives you an idea of kind of when people measure what the noise floor looks like in various parts of the spectrum. This is fairly low frequency, but you can see the difference between, for example, the city center, which is the top line here, and out in quiet rural areas. So you can imagine as you start getting into crowded environments and you start deploying all these devices, the noise floor is going to rise. So the question is, what do you do about it? And the answer is that you really need to be able to include interference testing as part of your testing at the outset. Again, very important for mission-critical devices to see how they perform. So testing tools need to be able to model various interference scenarios, and we will actually discuss, how we can do that. So again, testing the links. So I just showed you test before, rate versus range test, where you can say, well, how does my link work? That's great, but the real interesting question is, how does that look in the presence of all this other stuff going on? Before I show you a couple of tests, I just have a few little comments about, when people say, well, okay, so I want to do interference testing, what should happen? What should I be able to do? There's a couple of different ways to look at that question. There are some regulatory requirements actually around interference testing, the most obvious being radar. So what do you have to do in the presence of radar? There's, ETSI rules around that. And there are also some best practices. So these would not be actually regulatory kind of requirements, but things like there's an ANSI specification for coexistence that's used by certain industries or places where the deployers of networks might be concerned about how their devices will operate in the presence of other networks. So hospitals, for example, is a big one for this kind of coexistence test plan. They like to kind of set out rules for how devices should behave. The Wi-Fi Alliance did one as well for looking at Wi-Fi in the presence of essentially 3G, so LAA in the same spectrum. So again, not required, but at least kind of recommended. And then there's just basic performance, right? This would be what manufacturers, decide to do, how they think the device should behave in the presence of interference, and they make their own decisions and see if they can do something better than their competitors. So the way test beds like this, like ours, are able to do that is, I mentioned before, we have something called an interference generator. And the interference generator is able to generate interference, Wi-Fi interference, for example, on any channel with any sort of characteristic that you may be interested in. You can also generate interference that's not Wi-Fi, so things that look like Bluetooth or Zigbee, or even things that look like radars, for example, or microwave ovens, so kind of non-communication technologies. Chuck pointed it out before, but it's that guy hanging on the side of the box. It looks a lot like all of our other things. And so what we're going to start with, show a little demo here of co-channel interference. So what we're going to do is, looks very similar to the test from before. We'll run traffic between our access point and this PAL that's highlighted. And the traffic will go that way. But at the same time, as we're running that traffic, we're going to use the interference generator to inject traffic into the spectrum environment in this box. And when that happens, you can actually see what the link between the access point and the client device does. And so, as I mentioned before, you can actually see, hey, Chuck, are we
Yep, you're ready.
ready to go? You can actually see in some detail, which is a very useful thing about something like Can you start it again there, Chuck? I had
That's fine. Better to continue.
okay.
You ready?
Yeah. Okay, so what you're seeing here is traffic. So traffic is just running between the devices. This gives you kind of a baseline. And as we discussed before, right? You can see, you get all these statistics, right? So you can take a look at, the RSSI. You can see the data rates. The MCS. You can see the number of streams at 4, the bandwidth at 80 megahertz, and you can see what just happened here. The interference generator just kicked in, and you can see the throughput dropping by roughly half. And more interestingly, and this is what people who are kind of testing their devices like to do, you can look and see what kind of decisions were made here. So, for example, you can see that in this case, the bandwidth is kind of remaining steady. The number of streams has taken a bit of a hit. NCS has definitely fallen off over here. And the data rate, the data rate dropped because the MCS dropped. So you can see, all these kind of effects, and you can understand what's, people then use these to understand what how their devices are behaving in the presence of interference. I'm going to show you really quickly what the interference generator looks like. This is the interference generator. I mentioned before that you can look at all the devices via a browser. They all expose their own web-based interface, as well as the API that I mentioned before. And the interference generator can, as I said, either be a Wi-Fi interferer, and in this case, you can see that it's set up to generate 11 AC interference. You can pick the channel width. You can put what channel you want it to be on. You can set various other things, and even the priority, the QoS priority level of the traffic. And what you can do is replay a PCAP file. This is the way that works. We jump back here. So if you look, what happened now is the interference, when the interference generator turned off, the throughput recovered. You can see everything recovering back to normal over on the statistics side when the interference disappears. Chuck, you can switch over, by the way. Are you going to switch the AP? You can switch the AP now.
Oh, yes.
Okay.
Yeah. Actually, just real quick. One of the things, as Lee mentioned in the beginning, we're doing this with scripts, right? So I'm over here running, connected into the same system, and I fired off a script that created this test called throughput versus interference. It started the traffic, it waited 10 seconds, it started the iGen, and then Lee's just bringing that up again, as we mentioned, in the user interface. So we're capturing all that data in the database, plus giving you a visual of what's going on, and yet it's all run off Python scripts. It's all pre-generated. So the automation, as Lee mentioned, is a really key part of the system and how people interact with it more and more today. It's great that you've got the user interface, you can set things up, you can see what's going on, get your test set up, but then you don't have an operator sitting there for days and days running thousands of tests. You can automate all of it. And that's what we're doing here. That's why there's a little interaction between the two of us going on.
Yeah, I was just telling him to set up the next test. So as I mentioned before, the interference generator can be a Wi-Fi interferer, which is the test we just showed you. That was a co-channel interference test. It can also be as I said, a waveform generator. So it can emulate, for example, Bluetooth traffic, a microwave oven, as I said before, various other things. You can create your own. So this is a pulse type of interference, which is similar to what was done for the radars, except in this case you can actually build your own, right? So you can set whatever pulse width you want, the first repetition interval, the number of pulses, that kind of thing. You can also import your own file, create your own interference profile. But what I'd like to actually show you is the kind of testing that we can do for DFS. It's a very important test. People do it quite a bit. And I just need to, bring up a PAL here. Oh, bad news. Okay, so let me go back to the presentation. So here's what we're going to do. I'm going to show you how we can also do radar testing. So it's very similar to the tests that we've been doing so far, except in this case, I'm actually not going to bother running any traffic because the DFS test is really about the ability of the access point to detect the radar interference and then to vacate the channel. The way it vacates the channel is by sending out channel switch announcements to its attached clients. So it detects the radar, it needs to send out those channel switch announcements, and then it needs to move to a different channel on which it's not detected radar. And have you set it up? Okay. Channel 100. So Chuck has moved us to channel 100. And so what I'm going to do is use this PAL to capture a file to look at the packets that are coming out on channel 100. He tells me, and I'm going to use the iGen to generate radar interference, reasonably high level on channel 100. Okay. See if this works. Okay, so here we go. And we're on channel 100. Yep. All right. Trust you. So start capturing some packets. We can look here. I might have skipped over this before, but the other powerful thing about the PALs is not only can they be stations and access points, but they can also be packet sniffers, and we're using a PAL right now as a packet sniffer. I'm going to start. I've just started the interference, and that is probably plenty of time. So I'm going to stop the radar, and I am going to stop the packet capture. And when we capture those packets, we have it here. So this would be our capture.
Yeah, so while he's downloading that file, there are two modes there. One of them is capture packets on any device, right? There's a certain amount of memory that we capture packets on there, which is why there's the other option, which is streaming to the server. So when we're doing that synchro sniffer, we're sending multiple PALs worth of sniffer data to the server. That's all streaming to the octoBox server. It's capturing those PCAP files and synchronizing.
So we've also, in addition to some of this other work that I have mentioned already, we have been continuing to expand our ability to provide data analysis in addition to data collection. So we have a lot of tools that we find useful, and this is one of them. So this is a tool that we have that lets you do sort of automated PCAP analysis. So we just captured that PCAP file. We could open it up and look for channel switch announcements, but we have this tool which we can use to do that work for us. And he says, hoping that that will actually happen. So let me. So here's the PCAP file that we just did, and we just suck that in, and you can see that the analysis tool has actually scrolled through the file for us. It's actually dissected the packets, gone all the way into the the information in the beacon and found the channel switch announcements, and it's actually told us that the packets 422 through 429 were actually channel switch announcements. You can get some information about it, but it also tells you that you can see that we were on channel 100. I'm not sure why it's not telling us, and it's told us that we switched to channel 36. Did we switch to channel 36?
Sure.
You can see the count. So it sent 8 channel switch announcements, counting down from 8 down to 1.
Yep, we did.
We did? All right, so there we go. Can actually even verify that. But yeah, so that's how a DFS test works on our system. And it's really very convenient. We get a lot of people who use this test to make sure that they are able to adequately detect the radar types. We have all those pre-built radar types. Okay, so moving on from interference, I mentioned before that we have a lot of configurations which are quite a bit more complicated than even the ones that you're seeing right now in this room. And part of the reason for that is that mesh testing is probably one of the biggest topics that we deal with on a regular basis. There's a lot of interest in mesh testing, and the reason for that is pretty obvious, I think. Right? The reason is that it kind of comes back a little bit to even the IoT discussion before. Kind of everything is on these networks now. Everything is Wi-Fi enabled. So the old days of it was good enough to have coverage on your couch or something like that is no longer the case. People need coverage in the far corners of their homes in order to be able to make sure that all their devices are connected all the time. And that's being done more and more through the use of mesh networks and extender devices. One of the really useful things about a test bed like the one that we're talking about is that we can build up these systems that look a little bit like what I'm showing here, where you can actually connect multiple chambers together. And that's what's shown on the right-hand side here in essentially a full mesh configuration. So this is a little bit tricky to understand for people who haven't seen it before, but it's actually not that hard once you know what's being drawn and you can follow them. But what you'll find is that there's essentially a line connecting every box to every other box. So that's a set of RF cables, and they all go through an attenuator, meaning that you have essentially infinite control to change the topology of this mesh. And then on the left-hand side, what we have is a PAL device. Doesn't have to be a PAL, but can be. Is a PAL device being used as a client to the mesh. So imagine we have a mesh with a root node and 4 mesh nodes. The PAL can be pointed, again, by the use of the programmable attenuators at any box. So it can be here, and then by changing the attenuators, you can slowly move it to here. And so you can test the mesh performance, you can test roaming, you can test band steering, you can test client steering, you can test all kinds of attributes of these systems that are really important in these kinds of topologies. So, for example, this would be an example of a simple kind of string of pearls or linear topology. If you just put these attenuators at their highest values so that they're essentially, there's no communication that way, and the only communication is this way, then this PAL, when connected to this mesh node, the number 1 on the top, his traffic in order to reach the root node would have to go to 2 to 3, and from 3 to the root. So that's a simple kind of string linear topology.
And again, all of these lines represent 4 by 4, right? So this is a 4 by 4 backhaul.
This is a simple star topology. So here we have a root node that's connected to each of the mesh nodes, but none of the mesh nodes are connected to each other, so they can't see each other. and other topologies are possible, partial meshes, things like that. So when you're setting up systems like that, then what people are really interested these days is how their devices roam and band steer and things like that. So we'll show you actually two examples, if we can, of roaming and how roaming works in a test bed like this. The first one we're going to show you is a little bit interesting because we don't have multiple boxes here in order to separate out the devices. But the PALs themselves, if you think about it this way, are actually small, isolated, RF isolated environments. So they're kind of like small boxes themselves. So what we're going to do is we're going to treat these two PALs. I mentioned before the PALs can be stations, it can be access points. So far we've been using them as stations. Right now we're going to switch it around. We're going to use these two PALs as access points, and this other PAL, the one that's called 245, up on the top here, as a station. And we're going to roam it, that station, between the other two PALs. It's a little bit of an interesting demo, but it does kind of get the point across. So it kind of looks like this. So that PAL is going to start off connected to one of the APs, and then it's going to roam, and it's going to roam back. And I think we just need Chuck to give us the go-ahead. Giving us the go-ahead?
Almost.
Okay.
Sorry.
All right. Chuck promised that he was going to also learn jokes, so that for this part... Oh.
You might tap,
yeah, exactly.
Click the start button on the batch file.
Yeah. Are we ready?
Let's go now.
So anyway, what we'll see is the PAL connect to one of the access points, and then what we're going to do is we're going to essentially cross-ramp the other two. So we're going to change the attenuation so that the PAL starts off being close to one of the access points, and then we're going to move it far from that access point and move it closer to the other one, which is, in real space, it would be walking down the hall, and in attenuation space, it's just changed the value of the attenuator, and you can watch it move back and forth. And what you'll see is the throughput start off at a certain rate. It will dive as the AP moves farther and farther away. Yeah? All good? Okay. I don't want to talk over it because it's... No, I need to bring it up so you can see it happening. I can talk while it's happening. So it's connected now, and it's going to, as the you can see the attenuator ramping up here, and I will actually put up the statistics, full set of statistics over here, so you can watch it. You can see the RSSI taking a dive now as that attenuator comes up. The throughput is actually hanging on pretty well. At some point, it's gonna give up the ghost. Then the client will disassociate from the access point, and as it moves closer to the other access point, it's going to associate to that one, and you'll see the traffic pick up again. It's essentially a roam back and forth. And you can do this, there it goes. It's taking a hit now. And you can see all the other relevant statistics. You can see the data rates as they fall. The MCS plummets, the number of streams. Bandwidth is collapsing now. And that's it. You can see over the throughput has stopped. So this is, the iPerf session is now stopped because it can't get any throughput through. It's not associated. But if you watch over here, you can see the RSSI is picked up again. The reason it's picked up again is that it's now associated on the other access point. And pretty soon, there we go. There's the throughput back again. So it always does that. Not interesting, but I don't know what it is. But it will picks up again, so it's now attached to the other access point, and you're ramping it the other way now.
Yes.
Yeah. So you can see the throughput diving again. This is the kind of thing, again, people like to test. They like to understand how long it takes client devices to, give up a connection to an access point, how long it takes them to reassociate to another access point. And there's quite a bit more, well, I'll talk about that in a second, but there's quite a bit more detail you can get. You have this view, and you can also look in more detail at the PCAP capture of the entire roaming event, understand really what happened in great detail. I'll talk a little bit about that and point you to some places where we went into that in more detail than we're able to do here today. But you can see it now. It's lost the connection to that access point. It's going to come back. I'll let it come back. There, you can see it. Just showed up again as it roamed back to the other access point. All right, and now I think it just runs forever, so I'll stop it. And show you another one, which is kind of interesting. So this gets you a little more of a sense of how you can do the same. Do the same test with real devices. Again, we're limited here today just by the configuration that we have, but I do want to show you a real device test. And so in this case, what we're going to do is we're still going to use these PALs as access points. It's me, right? We still use the PALs as access points, but we have a phone in the box. Pick it up if you want. Yeah. And we're going to associate the phone to one of the APs, and we're going to do the exact same thing. We're going to cross-ramp the attenuators so that the phone sees one access point and then stops seeing it as well. And it will look like this, basically. I don't know if you see a little thing flashing AP1, AP2, but that's basically what you're going to see. You can actually see the phone move from one access point to another access point. So let's see if I can actually make that happen. Okay, first of all, sorry. Okay. So here's the phone. We're using the Android debug tools in order to actually view the screen of the phone this way. So this is the phone itself. It's actually already connected, it looks like, it says it's connected to access point 1. Yep, okay. No. Yes. Okay. So here we go. These are our scripts. So what this script is doing now is actually configuring the radios so that they will be access points, everything. That already happened in the last test, but it's just checking. So this is actually all that automation that we have been kind of telling you about, going through, configuring the access points, making sure everything is ready to go. And it is now cross-ramping. So let me quickly jump back over here. You can see it's connected to access point 1, and it's actually telling you the attenuation values in the 2 access points. So one of them is going from 0 and up by 5, and the other one's coming down from 90 by 5. You can actually see the signal on AP1 getting weaker and weaker, and that's gone. AP2 is here, and there we go. It just connected to AP2. And we can cross-ramp it the other way, and I'll just let you watch it this way. You can actually see it as it loses the connection to AP2. Boom, it picks up. Well, if there's AP1 connected yet? For whatever reason, Decides not to connect to AP1 this time. Yeah, should have. That's interesting. So anyway, half of that roam worked. I'm not sure why the other half didn't work, but anyway, we won't dwell on it. But that's the basic idea behind doing a roaming test with real devices. So, as I mentioned, we can actually get even much more detailed than that. We can actually look at a PCAP capture of a roaming event and look for things like association requests and response and disassociations. You can look at if you're using if the device is using 802.11v, for example. You can look for BSS transition messages. If it's an 11R, you can look for fast transition messages. You can look at all the details, see when all the packets arrived, and actually measure roaming time, much more precisely than visually by looking in detail at the PCAP file. So I showed you our little PCAP analysis tool before. I showed it for doing the channel switch announcements, but it also does some pretty nice roaming analysis as well. It'll look through, you tell it what client device it is that it's looking for. It'll look through a PCAP file and follow that client device through the file, and then look for, again, all the things I mentioned: association, disassociation, authentication, messages, BSS transition IDs, anything like that. So it'll find all that information, gives you kind of a nice plot of it, and will even then attempt to measure roam based on a couple of different definitions of what a roam is, when traffic last appeared on one AP and when it first appeared on another AP, or when the time between the last traffic message and the authentication frames, or whatever metric it is, does a number of different things. We don't have a lot of that here today, but we actually recently did a seminar on mesh and roaming, and it's all of that is actually on our website. There's links to it, and part of the reason it's interesting is that it's not just us. I mentioned also that there are a lot of different labs that use our test beds to do their testing, and we had a number of different speakers who are not from octoScope, one from a company called .11 Labs, one from SmallNet Builder, and one from DB Performance, and they all talked about different types of mesh and roaming tests that they do. Some of them do their tests in test houses, but then like to reproduce those tests in a controlled environment, make sure that what they saw is something that they can actually do in a repeatable way. So all that stuff is covered, and it's worth looking at if that's an area that's of interest to you. So, yeah.
That phone actually did finally connect.
Oh, we finally connected? Yeah.
But that's why you do it, right? I mean, we don't know why that phone is very slow.
Actually, it's usually faster than that, right?
Yeah, but that second connection has always seemed not as slow as that time. But earlier it was always seemed better in one direction than the other. Just not sure why.
Okay.
Something to dive into.
Yeah. So with all of this, I've been trying to sort of motivate one of the things that I want to talk about. So I've talked a lot about Wi-Fi 6, and I talked about roaming tests and things like that. So I mentioned that we have customers who are very interested now in mesh and roaming and building up systems like the one shown in this picture here with 4 boxes. We actually have much larger systems as well. And when you have many boxes like this and you want them all connected together, one of the things that happens is you start to need a lot of RF cabling. You need to be able to connect all these things together, and you need a lot of RF ports that takes up. If you then adding devices that are actually roaming, and then you want to add devices for sniffing, you can start to really run into a lot of RF ports. That's one piece of motivation. Another piece of motivation for what I'm about to talk about, which is a smart box, is that when people do like a rate versus range test like I showed you, where you have, let's say, an access point, and then you use a PAL as a station. For all the reasons I said before, using a PAL as a station is a great thing to do. It can be kind of a standard station, and it gives you a lot of information. But at the end of the day, we also heard from a lot of customers, yeah, but we also kind of need to test real devices as well. It's something we have to be able to do. And the only way to do that is to have another box for the real station so that it can be shielded, RF shielded. So those two things, maybe some others as well, but it's at least those two things are what moved us from the architecture that we have here, where we have these PALs in separate, kind of isolated small boxes that we attach on the outside of the box, to the smart box architecture, which I've talked about enough times that I think you kind of know what it is, where we have our PAL 6 that we already described embedded in the box itself. And the nice thing about that is that it gives you the ability to essentially sniff, the box can sniff itself. So without adding anything new to the box can look at any traffic that's going on in it, and it can be used as a sniffer. So the same way that I showed you a PAL capturing packets in that DFS test, you can use this PAL that's embedded in the box to capture all the packets that are happening in the box. You can also use that PAL just like a regular PAL by taking the signals out of the box and connecting them to another box through attenuators. So in a simple configuration like the one shown on this screen with these two boxes, we can do a number of different things. So this PAL can, for example, be used externally to talk to this AP in the upper box, and you can do rate versus range and things like that. Or you can actually use a real device in here, and you can have the access point talking to the real device in the box, and the PAL can be sniffing that traffic. So it's a very kind of compact and convenient way to build up test beds that have a lot more functionality than we were able to achieve previously. So again, I showed this before, so I won't dwell on it. That's what's in the smart box. That is the Wi-Fi 6, the PAL 6 module. And then the last thing I kind of really want to address in order to pull the whole story together is this thing I mentioned at the beginning, this synchro sniffing. So now, imagine test beds that look like this. We've got all these boxes. They all have these PALs stuck in them. We're roaming devices back and forth and up and down, and they're moving from AP to AP or from band to band or both at the same time or whatever it is. PALs are sniffing like crazy, and we have all this stuff, right? So we have, at the end of the day, we have a lot of traces, packet captures that we've captured in each of these boxes. And I also made the comment earlier on that we're trying to put a lot of emphasis not only on data collection, but also data analysis, making sure that people can understand all this data they're collecting. And this is a lot of data, right? So if you imagine that now you've got, let's say, 4 PALs in there, they're all sniffing. And at the end of this, you've got 4 different traces that then you would have to somehow glue together in order to understand what's going on in this roaming band steering event that you've generated. So we wanted to make that a lot easier, and that's what synchro sniffing is all about. So first of all, a new thing that we've done is we have implemented 1588 v2, so precision time protocol in all of our test beds starting now. So our server is a grandmaster, and all the devices will take time from that, synchronize their time to that clock. So all these PALs are time synchronized. And we've also created software that will collect up all of those traces and then use the fact that the clocks on those PALs are synchronized to use the timestamps in order to generate a single combined PCAP file. So it's a single time-aligned PCAP file that is made up of all of this stuff. So you can actually watch as the device, for example, moves through and moves from a root access point to a mesh access point, or from 5 gigahertz band to the 2.4 gigahertz band, or whatever it might be. You can see it happening and kind of easily follow it through the PCAP file. And by the way, what I mentioned before, the tool that we have, that PCAP analysis tool, then operates on these combined files to generate a plot where you can actually look, for example, at the client as it moves across bands, across access points, and watch all the signaling happen. So it's a much more convenient way to understand what's happening in these complex interactions. This is an example of one of these merged files. It's a, you can see that there's a probe ID that's been added, and it's telling you which PAL essentially has captured this packet. So you can see there's 2 here, sniffer 1, sniffer 2. In the middle of this roam, sniffer 1 and sniffer 2 are both active, and then later on it's kind of all sniffer 2. So we're going to try and do a quick demo of synchro sniffing. Again, we're not going to do a complicated roam because we don't really have the setup for that here, but we can show you the process actually happening. So what we're going to do is use the access point in the box to, well, sorry, we don't have to use it to do anything. It's already beaconing on both the 2.4 and 5 gigahertz bands. And what we're going to do is use 2 of our PALs to sniff those beacons and create a combined PCAP file. And then we'll stream that to Wireshark and hopefully see what's going on there. So, okay, hold on a second. It's like, no. So let's get rid of that. Right. All right, so I'm just starting the synchro sniffer, and I will start up my synchro sniffer over here. All right, and yeah, we should be seeing. So anyway, so this is what the synchro sniffer looks like. We're actually streaming the PCAP file into Wireshark directly, but for whatever reason, sorry, unfortunately, I'm only seeing the PAL 245. But this is what you would see generally. You see the PAL 245, and you also see the other PAL, the package from the other PAL streaming in here as well. We'll take a look at that a little bit later. For whatever reason, not seeing the PAL 5 packets. And I'm not sure why that is. Yeah, all of the 245 right now. But at any rate, roughly that is what the synchro sniffer would look like, and what you would be able to see. So finally, we're going to just close up here now real quickly by talking about, with all that stuff together, kind of what do configurations look like for Wi-Fi 6 testing, and all of the other things that we've been talking about. So I already kind of showed this configuration, the sort of two-box configuration with the PAL 6 embedded into the smart box. So what this allows you to do, as I mentioned before, is we have two sets of cables shown here, and the reason for that is that we want to be able to handle 8x8 MIMO over-the-air testing. So this is our 8x8 setup. You can do rate versus range in the same way that we showed before. You can add a turntable to this box. You can do rate versus range versus orientation. We'll actually show you a little bit about the turntable in a minute. You can do dual band rate versus range, because again, the PAL 6 is a dual band device, both 5 and 2.4. You can do real traffic and sniff that traffic. You can get all of what we call expert analysis in terms of the detailed statistics that come out of the testing, band steering tests, and shown up here again, I mentioned before, the light point unit for doing more detailed RF level testing. I had mentioned before that we worked together with LightPoint at the Wi-Fi Alliance to do those pre-correction tests. We also work with them even outside that context to use a concept that's very similar to that synchro sniffer concept to link together RF layer information, so EVM and constellation information, together with PAL captures, and go seamlessly back and forth between the two. And then, to, as I mentioned before, much larger, more complicated test beds that have a lot of the kind of the same components we've been talking about, but kind of many more boxes. So in this one, for example, this type of configuration can be used to do the sort of OFDMA or station device testing. So this is four client devices, for example, can be in here. We have this box is set up to do direct rate versus range testing against a device under test through multipath emulators. So this is also including multipath in it. The reason we have separate boxes in this setup instead of the single box that we had in the Wi-Fi Alliance testbed is that these boxes, as you will now recognize from having seen it before, are connected in a full mesh. So you can actually do mesh testing, roaming, band steering. So this is a much more fully featured testbed. It would allow you to pretty much test any kind of Wi-Fi wireless sort of configuration capability that you wanted to be able to test. So we've talked quite a bit about Wi-Fi in this. We did talk about Wi-Fi in terms of IoT, and I mentioned Bluetooth a couple of times, but one of the important things to mention, and it wouldn't really be very obvious from a presentation like the one I just gave, is that the testbeds are not really that protocol specific, right? Other than the PAL, which I've talked about several times. And the reason to bring this up is that the testbeds are actually fairly widely used to test non-Wi-Fi technologies. The only important thing is that those technologies need to operate within frequency band of operation that the testbeds can support. But anything from about 700 megahertz up to about 8 gigahertz is our traditional sort of typical method, sort of region, and that covers lots of different important protocols. So we have companies that test LTE. We're getting more and more interest in the United States in 3.5 gigahertz band, known as CBRS there. DSRC for automobiles, obviously Bluetooth that I mentioned before. And those test beds look like this. This is an example of a multi-protocol test bed. So what you're seeing there, and Chuck opened the door several times already and showed you, probably saw these antennas, these high gain antennas, those things there. Those support, pretty much any protocol. They're fairly flat in the 700 to 6 or 7 gigahertz range. But these are LTE antennas that are also mounted in the box, and this is a test bed that was used to do LTE to Wi-Fi handover testing by an operator. But that being said, so I just talked about whatever 700 to 8 gigahertz. There's actually quite a bit of interest that we get in millimeter wave testing. And the reason for that is that, it's a targeted band for 5G. And already talked about all the things that are going to be, there. And, the nice thing about millimeter wave bands, right, is that there's a lot of spectrum available. And so more spectrum means more bandwidth. You can get higher data rates, support all these applications that people are talking about for 5G. Also the wavelengths are much smaller, meaning that the antennas are small. So that's important for a couple reasons, right? We all know this, right? It can be hard to, roughly it's hard to get a lot of range at the millimeter wave bands. Just standard kind of path loss equations tell you that. It's hard, but it's not actually impossible. The reason it's not impossible has to do with the fact that the antennas are so small that you can actually have now a lot more antennas in a fairly reasonably sized space, and so you can actually do quite a bit of beamforming. Beamforming is a pretty important technology from the context of 5G, just in general. So what does that mean? That actually has quite a bit to say about the kinds of testing that people are doing in the 5G kind of millimeter wave area. If you've got devices that have, 4 antennas on them, even 8 antennas, you can get away with it. You can imagine doing only conducted testing. We always do over-the-air testing. It's kind of the point of our test beds is that we test over the air. But there are, people who test doing everything conducted, right? So they'll cable everything up. And you can imagine if you have a device like that, you can take off the antennas and run cables to them. Question is, what do you do when you've got, an antenna system that looks like that, right? 256 antennas and a thing this big. Those kinds of antenna arrays essentially make it impossible to do over-the-air testing. To do conducted testing anymore, right? So pretty much the vast majority of 5G millimeter wave testing is going to be done over the air because, again, it's very difficult to get to those antennas. It may not be possible in many cases. So to that end, we have been pushing our technology up into the millimeter wave area as well. From the foam anechoic point of view, we have been doing that testing, and we have started to create a box we call the box millimeter wave that's already in the hands of some customers, and it's really what you're looking at here. You can see kind of a multi-protocol version of this thing now with kind of 5G and LTE, and then millimeter wave antennas, which are different than the ones shown in here, but if you look where Chuck is going to point, you can see some millimeter wave things there, which I will not get into any detail about because we have a whole second half of the day to talk about this, and the team from Advantest will tell you much more about that than I can. The one thing I'll point out is the turntable. We haven't really talked about it. Turntable is kind of interesting from the point of view of millimeter wave testing. We use the turntable all the time in Wi-Fi for just being able to average tests over orientation. It sort of removes variations due to position dependencies or orientation dependencies between tests. Very effective for that. But from the point of view of millimeter wave testing, if you're really interested in beamforming, You can use the turntable also to move devices and see if they can maintain a beam on the millimeter wave antennas. So we have a lot of customers that we've been talking about doing that with. And so what we're going to show you, just to kind of end the day, is just a really quick test where what we're going to do is go back to the beginning, really, the rate versus range test. But this time we're just going to add the turntable into it. So you can see it look like that.
Maybe
I have quite as much stuff as that.
I just want to make sure we don't bump into that one. I'll show you. That's what you run.
That's what the you have to be careful about not catching stuff in it. Okay, so